the name of Almighty God, I'm Masa Sankoshi, and today I want to talk about model inputs. The temperature model input is always available. Select the source of the temperature for user-defined integer value expression for the temperature in the input field. This input option is always available. You can also select the temperature solved by a heat transfer interface added to the model component. These fixed physics interfaces are available for selection in the temperature list. Now I want to go to the volume fraction. Specify the phase volume fraction. Select the source of the volume fraction, continuous phase, or the source of the volume fraction, dispersed phase. When using a dispersed two-phase fluid diluted species coupling feature, the volume fraction is automatically coupled to the one computed by the mixture model interface in the same coupling. Now I want to go through the convection. If transfer by the convection is active, the velocity field of the phase in question needs to be specified. Select the source of the velocity field, continuous phase, or the source of the velocity field, dispersed phase. When using a dispersed two-phase fluid diluted species coupling feature, the velocity is automatically coupled to the one computed by the mixture model interface in the same coupling. Now I want to go through the diffusion. Use this section to specify diffusion coefficients describing the diffusion of each species in their respective phase. Use the source list to select the pickup diffusion coefficients defined in a material or chemistry interface. Select material and a fluid material to use the diffusion coefficient in a material available in the model. Is defined property groups, including a diffusion coefficient output property, are available for selection in the fluid diffusion coefficient list. Select chemistry to use a diffusion coefficient from a chemistry interface added to model input. Diffusion coefficients are automatically defined when calculated transport properties is selected on the interface level of the chemistry interface. All defined diffusion coefficients are available for selection in the fluid diffusion coefficient list. For user-defined inter-value expression for the fluid diffusion coefficient (DSC) of each species in the corresponding input field, this can be a scalar value for isotropic diffusion or a tensor describing anisotropic diffusion. Select the appropriate tensor type: isotropic, diagonal, symmetric, or full that describes the diffusion transport, and enter the values in the corresponding element, one value for each species. Now I want to go through the precipitation and crystallization multiphysics interfaces. The precipitation and crystallization branch of chemical species transfer contains interfaces used to simulate precipitation of a chemical species in a fluid solution and solve for the size distribution of the precipitate. The precipitation and crystallization interface and the precipitation and crystallization in fluid interface are multiphysics interfaces that combines the equation for mass conservation of dissolved species with equations for the size distribution of a precipitate. For space-dependent models, equations describing the velocity and pressure of the solution are also included. The size-based population balance interface can be used to compute the population balance of particles in a fluid. The interface solves for the discretized size distribution of particles, with support for gross and nucleation terms. For space-dependent models, transport through convection and diffusion are supported. Examples of the systems that can be studied include crystals in a liquid, gas bubbles in a liquid, and droplets in a gas. Now I want to go through the precipitation and crystallization interface. The precipitation and crystallization in the multiphysics interface is used to simulate precipitation of a chemical species in solution and solve for the size distribution of the precipitate. The interface is only available in zero dimension. The interface combines the reaction engineering and the size-based population balance interfaces. The precipitation multiphysics coupling is automatically added and coupled solute species with the size distribution of particles to ensure mass conservation. On the constituent physics interfaces, the reaction engineering interface solves for a variable number of species concentrations and reactions. The size-based population balance interface solves for a discretized size distribution used to represent the precipitate. The interface can solve for the nucleation, growth, aggregation, and breakage of particles. The precipitation and crystallization in full interface. The precipitation and crystallization in fluid physics interface is used to simulate precipitation of a chemical species in a fluid solution and solve for size distribution of the precipitation. The interface can be used for stationary and time-dependent analysis in two-dimension axisymmetry, and three dimensions. The interface combines the laminar flow, the transfer of diluted species, and the size-based population balance interfaces. The precipitation in the fluid-flow multiphysics coupling is automatically added and coops the fluid flow to the species transport and a size distribution of particles. The species transport interface solves for one or more multiple solute species in the reactants. In the precipitation process, the population balance interface solves for the transport and size distribution of the precipitate. On the constituent physics interfaces, the laminar flow interface solves the numerous equations for conservation of momentum and the continuity equation for mass conservation. The transfer of diluted species interface solves for a variable number of species concentrations. The species equations include reactions and transport by convection and diffusion. The size-based population balance interface solves for a discretized size distribution used to present the precipitate. The interface solves for the nucleation, growth, aggregation, and the breakage of particles, as well as transport by convection and diffusion. Now I want to go through the precipitation coupling feature. The precipitation multiphysics coupling can be used to simulate a space-independent system containing one or more solid species that are present in a precipitation process. The coupling feature adds an extra reaction to the precipitation and precipitating species to ensure mass conservation. Now I want to go through the settings section. The label is the default multiphysics coupling name. The name is used primarily as a scope prefix for variables defined by the coupling node. Refer to such variables in expressions using the pattern name.variable name in order to distinguish between variables belonging to different coupling nodes or physics interfaces. The name string must be unique. Only letters, numbers, and underscores are permitted in the name field. The first character must be letter. The default name for the first multiphysics coupling in the model is PFF1. Precipitant. Each species defined in the reaction engineering interface is available as a reactant in the precipitation and can be selected in the list. When a species is selected, an additional reaction rate is added to the species. The additional reaction rate is RPI is equal to rho P sigma V average J delta LJ SATIJ divided by MAP, where rho P and MAP is the density and molar mass of the precipitate, respectively. V average J is the average volume, delta J is the interval length, and STJ is the total source term based on the SI unit is 1 per quadratic meter second. For size interval J of the population balance defined as STR, J is equal to B0 sigma multiply Lj minus L0 minus derivative of J divided by derivative of Lj plus derivative of dnj based on Lj plus Sj. The reaction rate is added under the assumption that molar mass of the precipitant and precipitate are equal. When the size balance based population balance interface defines the nucleation growth or solution using the concentration and diffusion coefficient of the dissolved species. Additional fields may be available in equilibrium concentration in the equilibrium concentration field. Now I want to go through the precipitate. When couped with the transport of the diluted species interface into the precipitate, molar mass in the corresponding text field. When coupled with the reaction during interface, the molar mass field is only available when the molar mass is not defined in the reaction during interface. Precipitate section. Enter the precipitate molar mass in the corresponding text field. The molar mass field is only available when the molar mass is not defined in the reaction during interface. Now I want to go through the precipitation, the fluid flow coupling feature. The precipitation fluid flow multiphysics coupling is used to simulate a fluid flow containing one or multiple solid species that act as reactants in precipitation. The coupling feature accounts for the mass transfer of species and precipitate in the fluid flow as well as the consumption of selected species resulting from precipitation. Now I want to go through the domain level synchronization. The precipitation in fluid flow coupling feature synchronizes the features of the fluid flow interface with in the transport interfaces. When using the precipitation in fluid flow, the velocity field used by the transfer of diluted species is and the size-based population balance interfaces are synchronized to the one computed by the laminar flow interface. Now I want to go through the turbulent mass transfer. When a turbulence model is used, the precipitation in fluid flow coupling applies turbulence modeling for the population balance and species transfer interfaces in the following manners. Turbulent mass transport is added. The additional mass transport contribution is defined from the turbulent viscosity and a turbulent Schmidt number. For more information, see turbulent mass transport models. Mass transport wall functions are added if the turbulence model also uses wall functions. The coupling automatically adds wall functions for the mass transfer on the same boundaries as those defined by the fluid flow interface. For more information, see mass transfer wall functions. Wall functions are not added for the size-based population balance interface. Now I want to go through the settings section. The label is a default multiphysics coupling name. The name is used primarily as a scope prefix for variables defined by the coupling node. Refer to such variables in expressions using the pattern name and variable name in order to distinguish between variables belonging to the different coupling nodes or physics interfaces. The name string must be using only letters, numbers, and underscores are permitted in the name field. The first character must be a letter. The default name for the first multiphysics coupling in a model is PFF1. Now I want to go through the domain selection. The selection of the precipitation, a fluid flow coupling feature is automatically defined on the intersection of the selections for the coupled interfaces. Now I want to go through the precipitant. Each species is defined in the transfer of the species interface is available as a reaction in the precipitation and can be selected in the list. When a species is selected, an additional reaction rate is added to the species. For the added reaction rate, refer to the participant section of the precipitation interface. Now I want to go through the precipitate. Into the precipitate molar mass in the corresponding text field. Turbulence section. When the fluid flow interface uses a turbulence model, select an option from the mass transport turbulence model list. Case Crawford high Schmidt number or user-defined turbulent Schmidt number. For user-defined turbulent a Schmidt number, interturbulent Schmidt number, associated dimensionless turbulent mass transfer added to the concentration equation is defined as JTI is equal to minus micro T divided by Schmidt number and multiplied by delta Ci, where mu T is the turbulent viscosity defined by the fluid interface and the turbulent Schmidt number associated defined depends on the mass transfer turbulence model used. Now I want to go through the theory for the transfer of diluted species interface. The transfer of diluted species interface provides predefined modeling environment for studying the evolution of the chemical species transfer by diffusion and convection as well as migration due to the electric field. The physics interface assumes that all species present are dilute, that is that their concentration is low compared to a solvent, fluid, or solid. As a rule of thumb, a mixture containing several species can be considered dilute when the concentration of the solvent is more than 90% of molar due to dilution. Mixture properties such as density and viscosity can be assumed to correspond to those of the solvent. Thank you so much for watching my tutorial video on today. Today is the 18th of May 2026. Time is 12:12 p.m. Also, you can download the related Computer Multiphysics simulation software file from github.com/masterscript.